Okay, welcome. So we are now on part 3 of the Solow Growth Model. Last time we went through this stuff, we solved everything out analytically. So we found the steady states. We played with a ton of math. Hopefully it wasn't too much math to scare you away. I know it's like a lot of math to see this early on in the course, but don't worry. A lot of the math that you saw, you don't necessarily have to do. It's just important that you see the math. You understand the steps needed to get to the point that we're at. So it's not like you have to recreate a lot of that stuff. This time, though, what we're going to be doing is we're going to be graphing more stuff out. So all the analytical stuff that you saw in the last lecture, this time what we're doing is we're graphing it out. So we're going to see how it looks as a picture rather than just like a bunch of numbers or Greek letters. And from there, we can further analyze the steady state properties of the model. Now, we did that analytically last time. We looked at like, okay, if steady state capital is a function of, say, savings, total factor productivity, and depreciation. If one increases, if one decreases, how does that change steady state capital? Like we looked at all of that already. Now we're going to be doing the same thing, just graphed out rather than looking at numbers. So we're going to graph everything out, and then we're going to see what changes in savings, depreciation, and total factor productivity look like. And from there, we'll actually discuss what the sources of growth are in the model. And big surprise, hint, hint, it's not investing more in capital. It's actually things like getting new ideas, total factor productivity. So how are we going to solve this out graphically? Not all that differently from how we solve it out mathematically. So what do we do? Well, first we need to know what plot we're going to set up. So I'm going to set up a plot with output on the vertical axis, right? That's the dependent variable, so it needs to be on the vertical axis. And capital, which is the independent variable, on the horizontal axis, because output is a function of capital. And then I'm going to plot out that production function, yt equals at times kt to the alpha. What do I get? Well, I get this right here. So I get this nice upward sloping function, and y on the vertical axis, k on the horizontal axis. Okay, so now that I've got that graphed out, I need to graph investment next. But the question is, how are we going to do that? Because investment isn't like y equals, something kt. Investment is it equals kt plus 1 minus delta kt. There's no kt plus 1 axis over here. But you can remember there's different ways to express some of these equations. One of them is that investment is output scaled down by the savings rate S. So it equals S times yt, and S is constant, right? Households save a constant fraction of their savings every period, unless instructed otherwise. So if we have S times y, then we can also graph out S times at times kt to the alpha. And all we're doing is we're just taking that output, right? We're taking the production function and we're scaling it down by that constant fraction of savings, S. So we get this right here. So I have output and I have investment. And that's pretty cool. We've actually made some decent headway here. But the thing is, there's no way to get a solution here. What would the solution be? There's nothing intersecting, right? We don't have anything being set equal to anything else yet. So without any intersection, we're not going to be able to find any solutions. So we need something that intersects with this. And we can't just, pull a rabbit out of our hat and say, oh, hey, this is going to work. No, we need something that actually works, something that actually makes sense. So what would that be? Well, maybe depreciation's got something to do with this. And if you think about it, right, like we've got depreciation and we had steady state capital. And remember, when investment's not changing, all of a sudden that depreciation term seems to matter a little bit more because you've got, steady state investment equals KSS minus 1 minus delta KSS. Okay, maybe we're on to something here. So capital depreciates at a rate of delta per period. So each period, the amount of capital that depreciates would be delta times k. So I'm going to plot out a diagonal line, delta k, that has a slope of delta. Now, if you're like, oh, hey, fixed points and dynamical systems, what the hell are we ever going to do with that? Well, actually, we were going to do something with this right here. Because when you see this thing plotted out, you're going to go, hey, that's actually not all that different. And hey, good. Awesome for us. We're really happy with this. One, we know that we can find a fixed point because, well, we've got that diagonal line delta k with a slope of delta. Delta's less than 1. All right, but the thing is, the production function and thus investment, its slope is changing all over the place. There's areas where the slope is greater than 1. There's areas where the slope is less than 1. There's a point where the slope is equal to 1. What's going on with that? Well, it's a concave function, remember. So if we have this concave function, then there can be a solution in this case. So we're guaranteed that there will be a solution that exists, at least given the state of things the way that they are mathematically. Okay, so we can find an intersection, which is going to give us our steady state value. So let's plot out that delta k and see what we get. All right, so I've got delta k plotted out. Maybe its slope is actually equal to 1 or larger than 1 here, but in actuality, its slope is less than 1 because it has to be. So this is what we get. I now have output, investment, and depreciation. And I've got 2 points of intersection, excluding the origin, because we're not going to worry about that. So I've got a point here of intersection, and I've got a point here of intersection. So the question is going to be, which one is our solution? And then what's that solution going to be? Well, I'm going to give you a hint. If we've got delta k intersecting with at least one of these points, right, and you were to draw a dotted line down to mark where you are on the axis, what axis is that? That's the k-axis. So that's the k-axis. It's probably a good bet that we're going to be looking at steady state capital. So we're finding steady state capitals. Just the question is, which intersection are we going to be looking at? Which intersection's the right one? We got to think about that for a minute. It could either be where delta k is equal to y or where delta k is equal to I. And we're going to use investment. And why is that? Well, when capital reaches a steady state, it's when investment is constant over time. And then once we have that steady state capital where investment is constant, then that would imply a constant or a steady state of output. So we're going to look for steady state capital where delta k crosses the investment curve, thus giving us steady state investment. And from there, we'll get steady state output. So we identify that intersection as the location of steady state capital. So where delta k and I cross, that's steady state capital. We draw a dotted line down to KSS and a dotted line over to ISS. So at the KSS ISS point, that's where delta k and I intersect with each other. So now we've got steady state capital and steady state investment. And all we got to do is just draw a dotted line up from KSS to the production function. And we're going to label that YT axis as YSS, or steady state output. Now, when you think about when we found the steady state capital, or all the steady state values really, analytically, this is the same thing that we were doing. And if you were to go, all right, well, this is where this intersects, and it gives me this steady state, if you were to solve it out that way, you would actually get the same results that you got last week. So we're going to plug everything in, and we're going to get steady state output. Okay, well, here by plugging things in, all we're doing is just drawing a dotted line up. It's actually a lot easier. So we draw a dotted line up and then over, and bada bing, bada boom, we now have steady state capital, steady state output, and steady state investment. That's pretty cool. So now we just need to label what the shares of steady state output are. Which one is consumption? Which one's investment? So everything from KSS 0 to KSS ISS is steady state investment. So if we start here, KSS, work our way up to the KSS ISS point, okay, well, that's steady state investment. Everything from here to here is steady state consumption. And then if you look, okay, you add those two vertical amounts together and you get steady state output. So this is telling me steady state output is split up between steady state consumption and steady state investment, just like that resource constraint was telling us, y equals c plus I. So I just label everything from the k-axis up to that blue curve as investment, and then everything from that blue curve up to the black curve as consumption. And boom, there we go. We have now solved out the Solow model. But the steady state's not really all that we care about. We also care about like an equilibrium path. What do I mean by that? Well, this I totally stole from Daron Acemoglu. Equilibrium, that term equilibrium, is used differently in economics than it is in, say, like engineering or physics. In engineering and physics, it's used to describe a dynamical system at rest, like a dynamic equilibrium. But in economics, that's not really the case, right? Because in economics, there's like the market equilibrium that we need to be concerned about. And that's not necessarily the same as something being at rest over time. So if, say, the economy is away from the steady state, it would be in disequilibrium, according to the engineering and physics definition. But even in like a non-steady state, the behavior of the economy is still governed by market forces. So you're still going to have market clearing and optimizing behavior assumptions of the households and the firms. So even if we're not in the steady state, that doesn't mean the market isn't in equilibrium. The market is still in equilibrium. It may not be the best equilibrium that it could be in, but it is still in an equilibrium. Because, note, as we're solving this stuff out, you're not seeing like a supply and a demand, right? No, this is the steady state. This is like dynamic stuff. So we're assuming that the markets are still clearing even if we're not quite in the steady state yet. And the thing is, most economies are going to spend their time away from the steady state. Think like there's always some kind of shock that's hitting the economy, whether it's big, whether it's small. You know, the larger the economy gets, obviously the less likely it's going to ever be in a steady state, because you've got all these different agents in the economy. You've got all these households, you've got all these firms are constantly changing things, right? It's I hate using it in this context. It's like everything is dynamic. So, you know, with all these dynamic changes and whatever, right? We're not always going to be in equilibrium, well, in a dynamic equilibrium, but the markets will always be clearing. So even though most economies spend their time away from the steady state, we're really interested in like the entire dynamic equilibrium path, not just the steady state, like how it gets to the steady state. So let's say we're in a steady state, we move out of the steady state. How is the behavior going to be in trying to converge back to the steady state? So we need to look at the transitional dynamics of the equilibrium. Now, it's a difference equation because, well, there's, you know, differences over time and they're sort of all interlinked. So this is what's known as a difference equation. And let's say we start from some arbitrary capital labor ratio, and we're really interested in how the economy behaves as it gets closer towards that steady state. So given some like arbitrary endowment of resources, like, you know, you wake up one morning and it's Christmas and you got all this new stuff, right? That would be an endowment of resources. Think of this the same way. Everybody in the Solow economy wakes up one day and there's a certain amount of capital that they have. That is their initial endowment. That's their Christmas present, and they move forward from there. So the economy will follow that law of motion as it gets closer and closer to the steady state. Now, there's a lot of stability conditions required to make sure that this stuff happens. But if you remember everything from like the dynamical systems lecture, right, if that coefficient's less than 1, we have everything we need for a globally stable equilibrium steady state. And because of the stability of this dynamical system, the fixed point is an attractor. So if we move away from the steady state, we converge back to it, not away from it. And that is why I covered what I did with the dynamical systems and fixed points, to ensure that we do have stability of the dynamical system that we're playing with. And you don't need to prove it or anything like that. Just take my word for it. It is stable. If we move away from the steady state, we will converge back to it, not move away. So let's say in economics terms, right, if the economy starts out with too little capital relative to its labor supply, well, that capital labor ratio is going to be increasing. And this happens because households, people in the economy, are going to save more until they get to the steady state. So that marginal product of capital, hence the return to capital, is going to be falling due to diminishing marginal returns or diminishing returns to capital, and you're going to see an increase in the wage rate. Now, explicitly, you're not seeing this because I didn't show you anything with the wage rate, but this is just kind of what's going to be happening. If the economy starts out with too much capital, then they'll dissave, meaning they'll consume more, they'll save less, they'll invest less. The wage rate declines, and the rate of return to capital will increase. So if you start out with too little capital, right? Say you start out with K0. Okay, well, K0 and I do not intersect at all. There's a pretty substantial vertical difference between them. Okay, so we start at K0, we work our way up. And I need to wait for that thing to go away. Okay. Work our way up, and then we do that staircase zigzaggy thing that I showed you guys, right? Over and over and over. And we just get closer and closer and closer and closer and closer until we converge to K star and K star. Now look, here I've got KT plus 1 and KT on these axes. I don't have like KT and Y or anything like that. Why is that? Well, this is because I'm not looking at output as a function of capital. I'm actually looking at the capital decisions, the changing capital over time, in which case I need KT plus 1 and KT. So this is actually a lot closer to what you saw with the dynamical systems earlier, because remember you had like YT plus 1 and YT. Well, here we've got KT plus 1 and KT. And instead of this thing being this I curve being like, a straight line with a slope less than 1 to guarantee across with that 45-degree line, instead I've got a concave function. It starts at the origin. It's concave. Therefore, it's guaranteed to have some solution. So where K star equals K star, KT equals KT plus 1, boom, steady state capital. So if we start out with too little, we're going to work our way up towards steady state capital. If we start out with too much, same thing. We would work our way over. Just instead of starting out to the left of it, we start out to the right, and we do the little staircase thing, and we converge back to K star or steady state capital. So let's change delta. Let's change that depreciation rate here. If delta were to increase, what it means is that the capital stock in the economy is falling apart a lot faster. So we're going to look at it on the graph first, and then we're going to do some math later. But when delta increases, that depreciation line, delta K, is going to get steeper, meaning it pivots inward. Right? As it pivots inward, what happens is that steady state capital is going to decrease. Steady state capital falls, meaning steady state investment falls and steady state output falls. So if depreciation were to increase, the economy shrinks. And we can think about it intuitively. If you've got something that, you run some company, a business, whatever, and your stuff starts falling apart faster. You're like, what the hell? Like, I just bought this thing last week or last month, whatever, and it's fallen apart. Well, it takes more time, effort, resources, eventually money. We're not dealing with money in the economy just yet, but money will get introduced later. But it takes more time and resources to fix that now you can't put towards other things. So you spend more time and more resources fixing stuff that didn't need to be broken, that didn't need to get fixed because it shouldn't have broken. Thus, that is less time and resources available for investment in new things. So output is going to fall. So it says color purple lines. Oops, it was supposed to, I think when I was writing this up in LaTeX, I forgot to do the little slash to get that in there. But the purple lines represent steady states before the shift in depreciation, and the teal lines are the steady states after. And this is where we're first starting out. Okay, this is the initial equilibrium, the initial dynamic steady state equilibrium that we were looking at, steady state capital, steady state investment, steady state output. Okay, we got that. But now what we're going to do is we're going to shift that depreciation line inward. And as it shifts in, right, delta increases here. So that line gets steeper. Steady state capital falls from KSS to KSS1. Steady state investment falls from ISS to ISS1. Steady state output falls from YSS to YSS1. Now, when the depreciation line shifts inwards, right, that's the only line that moves. Output doesn't move, investment doesn't move. Why is that? Well, because there's nothing that is fundamentally changing output. You might be changing the level of output, right, but you're not doing anything to move the output curve. Changing the output curve, in this case, the only thing that would do that would be changing that A term. Now, what about investment? Why isn't investment shifting up or down? Well, investment's not shifting up or down because S isn't changing. If you change S, then investment will shift up or down. Output will stay the same, but if investment shifts down, you consume more and invest less. If output shifts up, you consume less and invest more. So you're not going to get a shift in investment just from a change in depreciation. Now, if A changes, that shifts output up and it shifts investment up by the exact same amount. So with a change in delta, you're not shifting Y or I. You're only changing that depreciation line. And you have to find the new intersection point between depreciation and the investment curve to label out your new steady state capital, investment, and output. So if you change depreciation, more stuff falls apart. You need to spend more time and resources to fix and repair what's falling apart, which gives you less to invest in new things for expansion of your business. So if investment or if depreciation increases, then the economy is going to shrink. Steady state capital falls, and steady state investment and output will fall. So how do we counteract that? What can we do if depreciation increases? Can we counteract that and try to get back to where we were before? Well, it all really stems from the law of motion of capital and the property that governs savings in the economy. Meaning, if depreciation were to go up, right, it's going to reduce capital in the sense that more of the new capital being bought goes towards replacing the previously existing capital that fell apart, which is bad for the economy. So if it happens, steady state output falls, and well, that kind of sucks. So is there anything we can do to get us back to where we were before? Well, the answer to that is, in fact, yes. We have to change how much we save. Say depreciation increases. Well, if depreciation increases and we want to get back to where we were, we have to increase our savings rate by the amount that depreciation increased. And when we do that, this is where the investment curve is actually going to shift up. And when the investment curve shifts up, that means that we consume less and invest more. So if depreciation increases, things start falling apart more, the society sees this and goes, hey, we all need to start saving. So they save more, they increase investment by an amount that will bring steady state capital back to where it was before, which brings steady state output back to where it was before. Now, when that happens, steady state investment will technically be higher because we have to invest more in order to get the same amount of output that we had before. And if we return to the same amount of output that we were at before, then when investment increases, consumption is going to shrink. So we can get back to where we were at the cost of consuming. So what does this look like? Well, looks like this right here. All right, so this is where we were last time. So depreciation changed, and we had that increase in depreciation. Steady state investment falls, steady state output falls, steady state capital falls. Looks like I was going in the wrong direction. Okay, here we are. So now we want to change the savings rate. When we change the savings rate, what we're going to be doing is we want to be able to get back to steady state capital over here, not over here. So what happens is we have to increase investment up to the point that it intersects with that new depreciation line. And when that happens, well, steady state investment increases substantially, but steady state capital goes back to where it was, steady state output goes back to where it was, and then steady state consumption is really, really small now. So this is what we get. So I shifted that investment curve up. So remember, whenever you change the savings rate, the investment curve is going to shift up. So when you change that, investment shifts up, we invest way more and we consume way less, but now output is the same as where it was before. So let's just increase the savings rate by itself, not in like a response to an increase in depreciation, right? So now we're just starting out with where we were before that depreciation change. And now all I want to do is just increase savings. Well, if I increase savings, I just shift that savings curve up. I increase steady state capital, and I increase steady state investment and steady state output. But if you look at the amount steady state investment increases by, that's a lot for a relatively small increase in steady state output. And this has to do with the diminishing marginal product of capital that we talked about, because it's increasing, but it's increasing at a decreasing rate. So if you put more capital in, hey, that's great, but you're not going to get as much of an increase in output. So changing the savings rate changes steady state capital, which increases output, but that doesn't translate into growth of output. So if we save more, it doesn't mean growth. It just means moving to a new point on the existing production function, or that existing curve. So we're giving up consumption to save more to increase output. So there's like trade-offs that we're facing, right? Because we're not, if you're getting growth, the idea would be you're increasing both consumption and investment. But if you're giving up more of one to get more of another, right? If you're giving up more consumption so that you can invest more to have higher output, that doesn't necessarily translate to like a good thing, right? That doesn't mean growth. It could be a good thing. It may not be a good thing. It depends. It really depends on what savings and depreciation are, if you remember the golden rule. So if saving more doesn't mean growth, what does mean growth? Well, that's the change in total factor productivity. Because we aren't interested in moving to a new point on the same output curve if we want growth. That just means, like I said earlier, we invested more and got slightly higher output. But that marginal product of labor, and the fact that the marginal product of labor is diminishing, kind of screws with us, because we're not getting enough of an increase in output to really trigger growth. If we want to trigger growth, we got to find a way to shift that output curve up, which means we're using the existing resources we have, but we're doing it in a more efficient way. And it lets us produce more and be better at doing that than before. Now, the thing is, none of the endogenous variables are going to be shifting that curve. So changing like capital isn't going to shift that curve. Changing investment won't shift the curve. The exogenous shift from A sub t will shift that curve. That's total factor productivity. If that increases, then it shifts the output curve upwards. So we need to think about what that is giving us and where it's coming from. So it's a shift in total factor productivity. I've said that like a lot, and I'll continue to say. You will likely hear total factor productivity like ad nauseum throughout this course. It makes output more efficient so we can make more stuff with less resources. And it happens like when somebody gets a new idea, you get a new invention, find a new way to make stuff in a more efficient way. Watch that movie, The Founder, right? The scene where they set up the McDonald's kitchen in the tennis court, and it's like the mock kitchen, and they pass, I think, like a ball around or something from one station to the next as like almost like a conveyor belt for a burger to assemble the burger in the most efficient way, right? Figuring that out would be a shift in technology, a shift in total factor productivity. If you're a Star Trek fan, go watch Star Trek First Contact. When Zefram Cochrane invents the warp drive, that's the faster than light thing that lets them fly all over the universe in Star Trek, or just really all over mostly the alpha and beta quadrants of the galaxy. That is warp drive. It's this combination of matter and antimatter to release a lot of energy, which creates a warp bubble around the ship, and then it moves space around the ship because, well, Einstein's theory of relativity, you can't actually move an object at even the speed of light, let alone faster than light, but you can move space, which has no mass, around the ship, and that's kind of what happens. It's like, think of like surfing, right? It's like riding the wave. Well, that would make things incredibly efficient. Imagine how easily we could do just about anything if we had warp drive. We could go to other planets and colonize them very, very quickly. We could extract resources from other planets, bring them back to Earth. We could, set up spacefaring civilizations. There's also the replicator in Star Trek, where you just tell this thing what you want, and it like makes it for you right there. Just kind of, it looks like the transporter, just like the little bzzz, and everything kind of comes together. So hunger would never be a thing. The need for drugs, for prescription medication, never a thing ever again. You just tell it, hey, I need I don't know, an antibiotic because I'm sick, or I broke my leg and I'm in a lot of pain. I need some painkiller for that. Well, it just makes it for you, and you don't have to spend a bunch of money anymore for it, right? That would make a lot of things much more efficient. Another example, that head massager thingy that I got for my pregnant fiance, soon to be wife, right? That made my life infinitely easier, because instead of me having to scratch her head, and then, my my hand gets tired and starts to cramp up after doing it for like an hour, I can just use this thing and just hold it over her head, just kind of move it around, and it massages it for me. She says she can really hardly ever tell a difference. I'm sure she's lying, and I appreciate that lie. But it makes my job a lot easier, which means she can get more head scritches. So I produce more happy fiance for less energy. So how do we do a technology shock? How do we model this? Well, what we're going to do is we're going to start with an increase in A. So if we've got our original output curve, we increase A, output, like capital will stay the same. Output moves because A shifts, right? No other input variables change. So what I'm going to do is we're going to shift from this black curve over to the blue curve, and that vertical distance of that shift is the shift in A, or total factor productivity. This is what happens when somebody gets a cool new idea that helps the economy. The economy can use that idea. They can use the same number of resources, but they get to produce more stuff. And this is what allows economies to grow. If you remember, there was like the Malthusian argument, Robert Thomas Malthus, who was an English economist, and he predicted something like that there would be like some kind of uncontrolled population growth, and that like the existing food supply wouldn't be able to keep up with population growth, and you would have like this population like crash or decline or something like that. And this was, I think, in the 17 or 1800s. It would probably help if I had researched that before I started talking about this, but the idea really popped in my head during the lecture. And there was something having to do with basically we wouldn't be able to sustain the number of people on the planet, and a bunch of people would die off and be this, awful, horrible, no good, very bad disaster. But he may have been correct, assuming constant technology. But in his predictions, and this is the reason why his predictions have failed, thankfully, is because technology changes came in place, and it made things, well, easier. Back then it was much more difficult to produce a large amount of food. Now it's fairly easy. Now, whether the food's any good for you these days is, a different subject of debate. However, you can at least get more food, and you can get it cheaper, and it's easier to get. Why? Because we're using the same number, or really in some cases fewer resources, to produce more food. Thus, if we have more food with this increase in population, well, the economy can grow. We can get more people, we can get new ideas, and we get people that are being fed. They're not, all starving to death. There was also the argument about like peak oil production in like the mid 2000s. Everybody was afraid that we were going to hit peak oil, and the amount of uh, like oil that was available was going to start falling and gas prices were going to increase and all that stuff. And well, that hasn't really happened. And, a lot of reasons for that. Fracking is one of them because we find alternative sources of energy when we need to. There are alternative technologies that we find. And when we're pressed, when we're like, hey, something's not working, or maybe something's not going to work sort of soon, we find other ways to make things work. You could also make an argument that the shift to electric vehicles is something of like a similar bent, that we have, we're going, hey, gasoline is, it's still kind of expensive. And all of a sudden, EVs are at least somewhat reliable and viable. I'm still not totally sold on them yet, but hey, it's an interesting path that we're on with that. So, as we see our technology increase, well, it's hopefully eventually one day going to be a cleaner source of transportation than the internal combustion engine, because, well, right now there's mining the metals for the battery. It's, kind of bad. And I think you actually have to get something like 70 or 80,000 miles on your EV before you actually start like getting like a net positive on the environment. But regardless, the idea is that we're getting new technologies that can allow us to produce more stuff ultimately at like a lower marginal cost. So that's good for us. It's really good stuff. So what does the shift look like? Well, it looks like this right here. So we shift the output curve up, and we shift it up by the amount that AT increases. So if AT increases from 1 to 1.5, well, then you just increase every point in that production curve by 1.5. And thus, by construction, you would also increase that investment curve by the same amount. So if output increases by 1.5, investment increases by, well, S times 1.5. So it'll, increase a little bit less, but that's that. And when output and investment increase, right, assuming depreciation stays the same, then steady state capital will also increase. Thus, you get an increase in steady state investment, steady state consumption, and steady state output. Literally everything grows. So that's the source of growth, and that's sort of how it looks like. Now, here's the cool thing about technology shocks. Capital depreciates, it falls apart, but ideas appreciate. So if you invent something, it doesn't need to get reinvented every time it gets used in the future, assuming, of course, like patents aren't a thing. But, for a lot of this stuff, you don't need a patent. You'd never need a patent for it unless you just directly want to rip off somebody's idea, right? You don't need to prove a derivative every time you use one. That would be a real pain in the ass. I mean, we would be very, very, very good. Everybody would be very good at real analysis if you had to prove a derivative every time that you used one. But you don't. You don't need to reinvent the wheel every time you build a car, right? The wheel's already been invented. All you need to do is just take that concept of the wheel, maybe make your own wheel, but you don't need to reinvent it because that idea already exists and everybody knows about that idea, right? That movie, The Founder, I highly, highly suggest you watch The Founder. There, the idea would be to use like a production line to make a burger for McDonald's, but that eventually got picked up by like Burger King and Taco Bell. They did so thinking outside the bun. So, hey, whoop-de-doo, good for them. Doesn't make visits to the bathroom after eating Taco Bell any more pleasant. But this is the source of growth in the Solow model. We get these new ideas and these new inventions that let us use existing resources much more efficiently. So, all that said, we've learned about growth. We've learned about the source of growth and, how these ideas come into play and what things look like, all that good stuff. So is Solow a good model? Overall, I got to say yes. One, it's still used as an intro model to learning about growth and development. And it's not just done in like undergraduate, it's even done in graduate schools. My first macro course in graduate school was actually the first probably month was spent on the Solow Growth Model. So if that tells you, and that was for a PhD level macro, so if that tells you anything about the importance of Solow, than good. But it does fall short in a number of areas. So you can kind of think of it as like you learn Solow to get the basics, but you also learn Solow in terms of like what not to do. The biggest area that I would argue Solow falls short is the lack of micro foundations. Now, in the real world, households make choices in the economy, right? Individuals make choices. You make choices every day about what to do in the economy. Solow doesn't assume that. Solow just goes, well, it's happening, but it's the choices are exogenous. They don't really matter that much. That's not really true, though. There's no objective function in the Solow model telling us how or why people make the decisions that they do. And when we get to the next model, you'll see what I'm talking about explicitly. But the idea is that just because it's macro doesn't mean that there aren't still individual people in the economy. In fact, a macro economy is just made up of a lot of individuals. Now, the influence of a single individual maybe matters a little bit less, but the influence of an individual still matters. We still need these people. We still need their objective functions. We need their like motivation, so to speak, to model their choices and to do so effectively. Now, what we typically do is we use something that's known as a representative household. Solow's missing this representative household, so there's a major endogeneity problem within the model, and this is something that got addressed by Robert Lucas in his Lucas Critique, which is a series of papers in like the mid to late 1970s, where he says that these models need micro foundations. We can't just move on without them. Now, this endogeneity problem, what is that? Well, it means really that we're modeling the chicken and not the egg. All right? If you model the egg and the chicken, okay, well, now you've got something. Now we got something here, right? But if you're just modeling the chicken, you're like, okay, great. Where did the chicken come from? Well, the chicken came from the chicken. But no, the chicken came from an egg. But you don't have an egg here. That's what is going on. So this is something that we're going to address in the next chapter when we touch the neoclassical growth model. And the neoclassical growth model is really just the Solow model with micro foundations added to it. Okay, so that's the first complaint that we have. And that's also the first thing that we're going to address in the next chapter. What's another problem? Well, there's exogenous growth that's assumed in the Solow model. And that's not really accurate. Now, granted, okay, all these things are like simplifying assumptions, right? Micro foundations, that was in all likelihood a simplifying assumption that Solow made. Exogenous growth, another simplifying assumption. And we got to remember, with these types of models, or just modeling in general, this isn't something that you just go, oh, hey, cool, I got an idea, and I'm going to make the best model right off the bat. That almost never happens. What usually happens is you develop a model, maybe it's a little simple, but it gives us some really, really good implications. And from there we go, all right, how can we make this a little bit better? And then 60, 70 years later, you go, oh, wow, okay, we made this thing a lot better. That doesn't mean it sucked for its time. It may not be the best thing to use now for implications, but back then, yeah, it was extremely useful, and it was a good stepping stone to get us to where we are now. Okay, sorry for that little rant. So exogenous growth. Well, we have exogenous growth in the Solow model, but I don't really think that's a very accurate or appropriate assumption to make. Because what we're really assuming is that growth just magically happens. Somebody just wakes up one day, gets this genius idea, and boom, we have growth. But like I was just saying, that's not ever really the case. You never just sit down and go, hey, I got this great idea, and boom, there it is. It takes time. It takes investment in human capital. So maybe physical capital, not so much, but investment in human capital, oh, very much so. There's also like research and development. Einstein spent years before he published his theories of relativity, and it was still years before Oppenheimer and others took some of those implications and put it to their own use. Solow, right, according to this model, would say that it just sort of happened overnight and without effort. But think about how much time Einstein had to spend, not just doing his research on the theory of relativity, but all the training he needed to be able to start that research. In real life, you have to make these investment decisions to be able to develop new technologies. Right? You decide to research something, that's great, but you got to give up other things to do it. You still face an opportunity cost, even though it's not necessarily with like physical capital, it's human capital. right? It's really the value of your brain. If you decide that you want to be an economist, you want to get a PhD in economics, I'd salute you for it. It was a lot of fun. But if you get your PhD in economics, you can't go get your PhD in physics at the same time because you're busy getting a PhD in economics. You can't go work a full-time job if you're getting a PhD in economics because you're getting a PhD in economics. It's going to be a lot harder to do other things if you're devoting a vast majority of your time to studying a PhD in economics, right? If you just go to college, even just undergrad, right, you're spending at least 4 years not working a job. And you do that because you perceive the benefit from doing so to be higher than the cost. So there's trade-offs that we face here, right? There's an opportunity cost. If you do something, you got to give something else up in order to be able to get it. We're going to address this in chapter 7. Now, another thing, perpetual growth. In the Solow model, growth happens once and that's it, right? You just get this nice little boost. The level of output increases once, but there's never really like a change to the rate. But if you look at if you were to just plot out output for a country, GDP for the United States, you'd see it's increasing at a constant rate. Like it's growing at a constant rate, but it's like exponential. You're not really assuming any chance for this thing to build on itself. But in reality, we've got exponential growth. You invent something, people can use your invention for their work, and everything continues to grow on itself. Solow doesn't have perpetual growth, but when we talk about chapter 6, we will be seeing some stuff with perpetual growth. Here's another problem. In the Solow model, technology explains 87% of output variation. So if you remember, if you've had statistics and you've learned about like linear regressions, there's like the part that you model, and then there's the error term, right? That error term explains 87% of the variation in output in the Solow model. Labor and capital only explain 12.5% of the variation in output. So that means that what you're modeling, the part that you're actually controlling for, is less than 13% of the variation in your dependent variable. Now, Bob Solow admitted that technical change was really any kind of a shift in the production functions. It could be slowdowns, speed ups, improvements in the education of the labor force that could all appear as technical change. And it's really best justified as like a measure of ignorance. But you don't want your measure of ignorance to be almost the entire bit of variation in the model. There were a lot of studies that tried to explain this and maybe try to find ways to fix some of this. A 1967 paper found the amount of variation that's explained by A was the result of measurement errors. So what they were doing is they accounted for movements along the production function. And when they do that, they find that total factor productivity accounts for less than 4% of output variation, which may actually make a little bit more sense considering that, economies grow at, relatively low rate, like developed economies grow at a relatively low rate. So, say 3-4%, something like that kind of makes sense. So overall, though, total factor productivity is a fairly contentious concept. It could be the result of poor measurement and a lack of proper application of economic theory. It could be more than that. So it's not like total factor productivity is this end-all, be-all, but in a lot of ways, it may very well be almost the best thing that we got. But, we're going to learn a little bit more about ways to have these technology shocks or have sources of shocks in the model that hopefully explain a little bit more the variation in output. But that's really for the next couple of chapters. But for now, we're done, at least for the Solow model. And we learned how to graph out the steady states. We learned, what the changes in the exogenous parameters give us, how we, look at changes in steady state capital, investment changes, what changes in depreciation will give us, what changes in the savings rate will give us, and then, of course, what changes in total factor productivity will give us, and that investing in capital alone isn't going to be enough to cause growth. And that's where total factor productivity comes in. And overall, that is, what Solow found in the development of his model is that, technology explains growth. Capital investment doesn't. Technology does. The extent to which technology is explaining growth, up for debate, but the fact that technology drives growth is absolutely undeniable. So with all that out of the way, this is a relatively long lecture. My apologies for that, but thank you for watching, and we will be starting Chapter 5, which is the neoclassical growth model, in the next video lecture. So thanks for watching. Bye.